Hi, welcome to video 8.7, L'Hopital's rule. And by the way, there is no S. Okay, so this is section 8.7. I know we're in chapter 3 right now, but it's something that used to be part of the AB curriculum, then it wasn't, now it is for the first time again in I don't know, 5 or 6 years. I've always taught it anyways because it's very easy and very useful. So, this is 8.7. We are going to be dealing with limits, and when we substitute, we're going to get either 0 over 0 or an infinity over an infinity. Now, these are called indeterminate forms. We've already dealt with you get 0 over 0, and we factored, or we rationalized, or we simplified. We haven't dealt with infinity over infinity or negative infinity over infinity yet. There are other indeterminate forms in this section, but those are for AP Calc BC. So, here's what L'Hopital's rule says. It says, if you have a limit of a fraction, okay, it's going to be a fraction, some kind of rational type function, the limit is x approaches c or x approaches infinity or negative infinity. But you substitute and you get one of these 5 situations. You get 0 over 0, you get infinity over infinity, negative infinity over negative infinity, etc. If that's what you get, and only if that's what you get, then L'Hopital's rule says that that limit that you had is equal to the limit as x approaches that c of f prime of x over g prime of x. This is not a quotient rule. It's what everybody wishes the quotient rule was, but it is not the quotient rule. You're actually going to this time take the derivative of the numerator over the derivative of the denominator. So here's an example. Do you remember when we learned that formula, we knew that that was equal to 1. You don't have to memorize that anymore, because if you substituted, you'd get sine of 0 over 0, which is 0 over 0, which allows you to use L'Hopital's. Now, when you're doing work for this, you've got to show that it gives 0 over 0 or an infinity over an infinity. You have to show that. You also have to let the reader know that you're about to use L'Hopital's. You can do LOP, that's fine. So, since it's equal to 0 over 0, then that original limit, we can now take the derivative of the numerator over the derivative of the denominator, which will give us cosine x over 1. Now when I substitute, I get cosine of 0, which is 1 over 1, and there's my answer of 1. You'll also remember we had dealt with this formula, limit as x approaches 0, 1 minus cos x over x equals 0. You don't have to memorize that anymore. If you substitute, the cosine of 0 is 1. 1 minus 1 is 0. Replace x by 0. You get to use L'Hopital. You have to show both of these things in order to earn full credit. Now that you can use L'Hopital's, it's the limit as x approaches 0. The derivative of 1 is 0. The derivative of negative cos x is negative sine x, and the derivative of x is 1. Now you'll substitute again. You'll get the sine of 0 over 1, which is 0 over 1, which is 0. Now, if you remember, this was very difficult to deal. You had to introduce and counteract. All that's gone. Plug it in. You get sine 0 over sine 0, which is 0 over 0. Get to use L'Hopital's. Derivative of sine 3x is cos 3x times 3. Derivative of sine 2x is cos 2x times 2. You're going to substitute x equals 0. You'll get 3 times the cosine of 0, which is 1. 2 times the cos of 0, which is 2 times 1. Your final answer, 3/2. So, if you look at numbers 5 through 10, it says evaluate the limit A using techniques from chapters 1 and 3, B using L'Hopital's. So what will happen in these, you'll get a 0 over 0, and you'd be able to, for example, here, factor in, cancel, rationalize, etc. Okay? So, if we look something like number 6, a rational function, if I substitute, I get 0 over 0. When we started this course back in September, we said that if you get 0 over 0 when you substitute, then you will factor. And sure enough, the top factors into 2x minus 3 times x plus 1. The x plus 1's cancel out. Substitute x equals negative 1, you get negative 5. The other way of doing it, which is faster, is to go, oh, look, substitution yields 0 over 0. I can use L'Hopital's. It's equal to the limit as x approaches negative 1 of the derivative of the numerator over the derivative of the denominator. Substitute in x equals negative 1, you get the same answer. Same idea here. Doing it with part A, you'd have to do all that, pull out the 1/2 and introduce the 1/4 in the bottom here, so you'd have to counteract with, it's a big problem. But with L'Hopital's, you plug it in, you get 0 over 0, right? Sine 0 over 2 times 0, you get to use L'Hopital's. And, whoops, sorry, over here, you get 0 over 0. Derivative of sine 4x is cos 4x times 4. Derivative of 2x is 2. And now you substitute, you get 4 times the cosine of 0 over 2, which is 2. The 2 goes into the 4 2 times. Cosine of 0 is 1. Your final answer is 2. Okay. Now, we need to talk about this a little bit. If you take a really large positive number and add to it a really large positive number, I would hope that you would agree we'd get an even larger positive number. But infinity minus infinity you might think is 0, but the answer is that it's indeterminate. And the reason is because this could just as well be 1,010,000 minus 1,000,000, in which case the answer is 10. It could be 1,000,000 minus 1,000,000,000, in which case the answer is negative 1,000. I mean, or negative 900 million, etc. So because we don't know the relative sizes of these infinities, we cannot make a conclusion. It's indeterminate. 0 times infinity times infinity will give infinity. You have a large positive number times a large positive number. You'll get an even larger positive number. Infinity over infinity, also indeterminate, as we just saw. Again, that could be 2 million over 1,000,000, which is 2. It could be 2 million over 30 million, which approaches 0, so it really could be anything. A constant times infinity, well, if the constant's positive, it'll give positive infinity. If the constant's negative, it'll give negative infinity. Okay, so here's number 10. At this point, it's just saying evaluate the limit, use L'Hopital's rule if necessary. Whoops, sorry, that wasn't number 10. Number 10 was this one, but this, whatever. We're using L'Hopital's rule. So we plug in, we go to infinity, so we have 2 times infinity, which we agreed is infinity, plus 1 is infinity. 4 times infinity squared is 4 times infinity, which is infinity. And infinity plus infinity is infinity. So I do get infinity over infinity, and therefore I can use L'Hopital's. Take the derivative of the numerator, you get 2. Take the derivative of the denominator, you get 8x plus 1. Now when you plug in infinity, you'll have 2 over infinity, which of course is 0. Now, we already knew that was going to be 0 because this is a rational function. This is the end behavior, and it does have a horizontal asymptote of 0 because the degree of the top is less than the degree of the bottom. Now, this is like 14, and now it gets a little tricky. When you have radicals, you're really going to want to avoid L'Hopital's because L'Hopital's takes the derivative of these things, and the derivative of an integral is very hard to deal with. So, if you say, okay, let me plug it in, so 4 minus 2 squared is 4 minus 4 is 0 squared is 0. Replace x by 2, I get 0 over 0. Now, you would think that you could do L'Hopital's, but you really don't want to do L'Hopital's, okay? Just the derivative of the numerator itself alone has all this stuff going on in it. It's really not something that you want to do. So the best way to do this is the old-fashioned way of doing this, which is to factor the 4 minus x squared and get 2 plus x times 2 minus x. Break up that product. Rewrite the bottom as negative parentheses 2 minus x. You now have 2 minus x to the half and 2 minus x to the 1. And then so you have 1/2 minus 1, which is negative 1/2. So it ends up as the square root of 2 minus x on the bottom. There's your 2 plus x to the half on the top. There's your negative sign. And at this point, the limit as x approaches 2 from the left. 2 plus 2 is 4. Square root of 4 is 2. Negative 2. And 2 minus 2 is 0. Now, whenever you get a non-zero over 0, since the numerator is negative and this denominator is approaching zeros through positives because it's approaching a square root, and therefore you get negative infinity. Now, L'Hopital's can be used repeatedly, so it's possible that you'll get 0 over 0. When you substitute, you'll use L'Hopital's. It's possible you'll get 0 over 0 again, and you'll substitute, get 0 over 0, do L'Hopital's again. It can happen a few times. So I wanted to give you an example of how that works. So here's an example I made up. If I plug in 0, sine of 0 is 0. 0 squared is 0 minus 0 squared over 4 times 0. So we get to use L'Hopital's. Derivative of the top is 2 times sine x times cos x by the chain rule, minus 2 sine x. And I take the derivative of the denominator, which is 12x squared. Well, if I substitute again, I get 2 sine x cos x is 0, minus 2 times 0 is 0 over 12 times 0 squared. So this is the key thing right here, and this is so important. And let me emphasize that. If I can do this here, I don't think I can. Okay, what I'm going to do is this. There we go. Simplify. Always simplify before you do L'Hopital's again. Now, you may or may not notice that 2 sine x cos x is the sine of a double angle. But if you do, it's going to make the rest of the work a lot easier. So, I know it's going to give 0 over 0. I just simplified it. So now I'm going to get to use L'Hopital's again. Derivative of sine of 2x is cosine of 2x times 2 by the chain rule, minus derivative of 2x is 2, derivative of 12x squared is 24x. If I replace x by 0, cosine of 0 is 1, 2 times 1 is 2, 2 minus 2 is 0, 24 times 0 is 0. So I get to use L'Hopital's yet again. And so I take the derivative of the numerator, which is 2, times negative the sine of 2x times 2, minus 0 over 24. And now if you replace x by 0, the sine of 0 is 0, negative 0 is 0, 0 times 2 is 0, times 2 is 0, divided by 24. All that work to get 0. And that's the end of video 8.7.